Hi guys, so we'll be starting off with looking at um, more such examples of chiral center. So let me just define briefly the definition of chiral center. Chiral center. So chiral center is four different groups attached to atom. So the atoms, the atom can behave as a chiral center. Four different groups attached to a atom. Okay. So in a sense that for carbon atom, then this implies that sp2 or sp hybridized atoms cannot be chiral center. Okay. So now let's have a look at some of the examples and determine whether they are chiral center or not. So let's have a look at examples. We have this and this. Okay. And let's have a look at that how many chiral center this compound has. So if you look at this carbon and this carbon, because rest of the four carbons are not chiral centers, because given that all of them have two substituted hydrogen atoms. Okay, so let's have a look at how many chiral center this compound has. Okay, so on this you can see that if you go by this, so you can find 1 2 3 third at the third position you find a oxygen atom, and in this if you go anti-clockwise you will find at third you have a carbon atom. Hence these two groups are different, so this is a chiral center. What about this? Same, if you go at the second carbon from this end and you go from the second carbon from this end in anti-clockwise direction, you find chiral center also exists here. Okay, and the two other groups are obviously hydrogen and uh, this the upper going carbon chain, and for this carbon again hydrogen and the lower going carbon chain. So two chiral center can be found for this compound. So let's have a look at this. uh, so we have, and why oxygen is not a chiral center here? Because oxygen, if you see clearly, it has two lone pairs, so two same groups, hence it will not be the chiral center. So in this compound you have to identify the chiral center. So what would be the chiral center here? This and this. Okay, why? Because when you look at this, that when you go anti-clockwise from this carbon, you find carbon at second position and a ring or continuing it. Okay, if you go from this, you have carbon at first position, and if you go at this, you have one substituted carbon at first position, and then the ring continues. So both and fourth is the hydrogen. So all the four groups for this chiral center are different, hence this will be a chiral center. And similarly I can also say for this, because it's a symmetrical, so two chiral centers are there. So before that, isotopes will also act as a group in chiral center. So if I have means H and D and T attached to a atom, or uh, attached to atom, then we will say that okay, these groups will be considered different and it will exhibit it will be chiral center. So and one more thing, if We just saw this example in the last video lecture, that if lone pair of nitrogen is involved in resonance, then it will be not be counted as a chiral center. Counted as a chiral center. Why? Because when it is actually in resonance, then it is converting itself from sp3 to sp2 hybridized nitrogen atom. Hence, once it is getting a sp2 character on itself, it will not be considered as a chiral center. So next question comes that you have to identify the chiral center in the following compounds. Okay, so we have this and this. So what would be the chiral centers in this compound? Only this. Why not this carbon, not this carbon? Because they are sp2 hybridized. Let's look at second example. We have this and this. So what would be the chiral center in this compound? This carbon atom, this carbon atom, this carbon atom, and this carbon atom. Why? If you go and look at numbering the carbon, on first we find a carbon atom, on second we find carbon atom attached to this ring, and here we find a carbon atom and second carbon atom and the third carbon atom. So on the second we are finding 1 2, on the third we are finding for this carbon atom, on the second carbon we are finding a ring going, but on the second carbon here we are finding two substituted H. So this group and this group is different. Similarly, how we are finding at the first and second we are finding two substitutions going from one is going to complete this cyclohexane ring and other is going to complete the this 6-member ring. 1 2 3 4 5 6-member ring. Okay, so this is also different. Hence, if this is exhibiting exhibiting as a chiral center, so similarly all the four will be exhibiting themselves as chiral center. Let's look at third example. So what will be the chiral center here? Will this be a chiral center? No. Why? Lone pairs are involved in resonance. Will this be a chiral center here? Yes. Why? CH3, this group is different. It has also substituted H, nitrogen atom. So let us look at the chiral center in this compound. What are the chiral centers in this compound? Obviously this and this. Why? Self-explanatory. Okay, so let's have a look at this compound. Whether we have, which chiral centers do we have in this compound? This one and this one. And what are the chiral centers in this compound? This one and this one? 0. Why? If you go from this side and you go from this side, these two are the same groups attached to this carbon atom, and similarly for this carbon atom. Hence, both are not chiral centers. Answer would be 0. So let us look at the last example. We have this and CH3 attached here. So what is the chiral center here? This would be chiral center, this would be chiral center, and this would be chiral center. So 3 chiral centers would be there in this compound. Okay, so now let's have a look at what are enantiomers. So enantiomers are stereoisomers which has non-imposable mirror image. Okay, so let me write down the definition first. Stereoisomers which has non-superimposable mirror image are called enantiomers. So what do I mean by non-superimposable mirror image? So if you look at this carbon, we have, let's suppose this hydrogen is going inside the plane or away from your face. This is in the plane, this also is in the plane, and this is coming out of the plane or towards your face. So if you draw the mirror image of this compound, you would find that something like this would be the structure, CS3 and ET. So now if you try to superimpose both the two compounds, so you would not be able to do it, right? Because when you are going to superimpose them, one would be hydrogen here, and on the same carbon hydrogen would be, if you try to superimpose, hydrogen would be here. Similarly, if you try to superimpose OH, then OH for this carbon atom would be here, something here, and OH for this carbon atom would be here. So these two are clearly not superimposable. Okay, so this is called a wedge dash formula, and these two compounds actually exhibit same physical property. Okay, so now let us, before proceeding further, let us see what is R and S system. Okay, so R is actually what is called the rectus, and S is what is called sinister. Okay, so rectus is clockwise and sinister is obviously anti-clockwise. Okay, and what do I actually mean when I say that R and S system in chiral compounds? So we'll just look into it. So let me draw an example for the same. So if we have carbon OH, H here, CS3 and ET. So let us actually number the groups attached to the carbon atom based on the priority rule. Okay, so this would be the first priority, second priority would be ET, third would be CS3, and obviously fourth there is no need to mention the fourth one. So from first to second we can draw a circle like this, from second to third circle goes like this and completes on the fourth. Okay, so this is a clockwise circle formation, or from source we reach the destination with a clockwise movement. So this is a R configuration, and on the other side, if we were to draw the mirror image of this compound, it was something like this, it was non-superimposable on the previous one. So it would have priority wise, first priority here, second priority obviously here, third here. So if we draw from first priority to second priority to third priority, it is in anti-clockwise direction. So this is S configuration. Okay, so mirror image or enantiomers have opposite RS configuration. Okay, so let's look at some more examples of drawing RNS configuration of some more enantiomers. Okay, so before that, an important property that enantiomers have same physical properties such as melting point, boiling point, and stability. So enantiomers have same physical property such as boiling point, melting point, and solubility. Okay, so now let us look at some of the examples in wherein we want to calculate the RNS configuration of various compounds. So this is a compound. So let us mark them with priority. I hope you understand what do I mean by priority. Means we've already seen how do we calculate the priority of attached atoms on a particular carbon atom or a chiral center. So using the same, we are calculating the R and S configurations. So these are basically the priority which we set in our EZ when we were looking at EZ priority rules as well. So in this case also the priority rules remains the same. Okay, so I would be at highest priority, second would be Br, third would be obviously chlorine. So we can draw a circle in clockwise direction, hence it is R. Let's look at another example. Here we have chlorine. Chlorine is at away from the plane. So yeah, we have bromine, we have iodine and fluorine. Okay, fluorine is coming towards the face. Okay, so what if we change the, obviously this is an S. Why? Because first comes here fluorine, first is the iodine. Okay, second is obviously the bromine, third is chlorine. So this is R, sorry, I beg your pardon. So this is R. So what if we change the positions of, let's say we exchange the positions of fluorine and iodine, and then iodine and chlorine. So these three atoms position I changed. So it would be something like, if fluorine comes here, bromine comes here, iodine comes here, and chlorine comes here. So what would be the configuration of this enantiomer? Again, first, second, third. So if we again draw the structure, it would be something like this. So it would be S. So what's the issue we are facing here? So the issue we are facing here is when we change two even bonds, or we change two pairs of bonds or groups attached to this carbon atom, when fluorine is in away from the position, we have an S configuration, but if chlorine is away from the position, we have an R configuration. But we know the fact that in the rules, we'll just be discussing the rules of having the RS configuration, but in the rules, when we change the even pair of groups, then the configuration must not change, right? So are we facing some confusion here? Obviously yes. So we calculated R wrong here, and the reason for wrong calculation is we didn't put the least priority group in the dash bond. The rule is the least priority group among all the four groups should be away from the viewer, but in this case it is towards the viewer, hence this configuration is not R, this is S. Okay, so let us first discuss the rules before going to the next topics. So the rules for RS configuration in dash formula. Okay, so first is groups around the chiral center are arranged in their order of priority. In their order of priority. Okay, second point is higher atomic number will be given high priority. Okay, the third one is fourth group or the least priority group must be away from the viewer, then only we can apply RS configuration. So fourth group must be away from the viewer, then only apply RS configuration rules. So this brings us to the end of this lecture. In the next lecture we will be seeing more such examples on RS configuration of different compounds. Till then, good luck and goodbye.